Salam sir.
Okay, in this week we will study about another topic. So this is will be the last topic of your math lab, numerical integrations. So it is only taking about 1 hour. It's a very short topic. So I think I just go through to the lecture notes so that you can see what is the topic is all about. Okay. So in this week, we will study about numerical integration by using Octave or MATLAB. Okay. So I think most of you knows about integration. Okay. Integration is symbolized by this symbol. And in your experience, you should know that any integration will have certain lower limits value. They say I put it as A, and upper limits of integration value, I will use the symbol of B, and you need to integrate certain function that you want. Let's say in this case it is fx with respect to the variable they want to integrate, which is x. Okay, so in your mathematics course, maybe some of you have discovered how to solve this simple equation, and let's say this integration of x dx. Sekejap. Halo. Ya. Okey, kalau besok. Okey. Okay, sorry for the interruption. Okay, so we continue back to this example, which is you want to find the integration of x dx. So you will use the formula that you studied before, which is x to the power of 2 over 2, and you have to plus certain integration constant c. And maybe you have also studied about how to integrate trigonometric functions, and you can refer to any textbooks of mathematics. This will be negative cos x plus c. Yeah. So these two examples are the simple example where you don't need to use any numerical approach. You just only analytical approach to solve the integration. So where we will use numerical approach, okay, if let's say I want to integrate a function like this, okay, so you will be in a problem here because the function that you want to solve here is quite complicated, and you cannot use any techniques that you have learned in your mathematics to solve this integration. So in order to help you to get the solution of this, we have to perform numerical integration either by using manual computation, or you can use computer approach, where in this case we will use Octave or MATLAB. Okay, so due to that, so our lesson learning outcome will be to study about 3 different numerical approach in integrations. The first one will be the trapezoidal rule. That is the first simple method to approximate that integration. Second one is to use Simpson 1/3 rules. And the third one is to use Simpson 3/8 rules. Okay, so all of this can be subdivided into 2 methods. For trapezoidal rule, you can use the simple one called as single trapezoidal method. And if you want to have a quite accurate solution, you may use multiple trapezoidal method. So similarly, for these other two methods, you have also single and multiple. Specifically for Simpson 1/3 rule, and the same thing goes to Simpson 3/8, where you have single and also multiple. Okay, so in total you will have 6 methods in this topic to solve the integration. Okay, before we proceed, just want to know, can you hear my voice clearly? Is there any lagging? Does the video is very clear that you may see?
Yes, sir.
Yes, sir.
Yes, sir, clear.
Okay, alhamdulillah. Okay, this is my roadmap in order to understand this topic. First of all, we have to know the definition of integration, and also what is the interpretation of this integration. Right? So once we know this definition and integration, then we can appreciate the method that we want to learn after this, which involve the single trapezoidal rule, multiple trapezoidal rule. You have also single and multiple Simpson 1/3 rule. And last one, which is the single and multiple Simpson 3/8 rule. Okay, each of the methods we will understand the mechanics of the solution, and we will develop the formula on how to compute the integration based on each of these methods. And at the end of the presentation, I will demonstrate one example of integration that you will use Octave. So we will use Octave to code all of the equations that we have for trapezoidal, Simpson 1/3 rule, and Simpson 3/8 rule to compute the integration of the given problem. Okay? That will be the our plan for this lecture. Okay, as I said before, we have to know the definition of integration. So basically, most of you knows about this. This is the definition of integration in the mathematics equations, where you have the lower limits and upper limits, right, which is A and B. And you need a function here that you call as integrand, right? So this function, we call it as integrand function, a function that you will integrate with respect to your variable, which is in this case is x. And in this topic, the solution of this integration, we will use I to denote the solution for the value of the integration. And what is the interpretation of integration? The interpretation of integration is only to find what is the area. What is the area that is underneath the graph, where your graph is y is equal to fx, that is bounded from lower limits, which is this one. So let's say this is your lower limit, x is equal to a, and this is your lower limit of integration, and bounded by another line that we call it as upper limit of the integration. Okay, so the area is bounded by this curve, y is equal to x, as you may see that, and silently, it is bounded also by this line that is given by fx is equal to 0. So how do I include this fx equal to 0 in the original equation? If you see carefully, your equation can be written in this form, where your 0 is silently written there, and that's why you may see that this y equals 0 is also the boundaries that bounding the area that you want to find the area by using the integration. So this is the area that you need to compute based on this integration exercise. So that is meant by integration. Is only to find the area bounded by this curve, that is silently stated in the equation, and by this lower limit, and also by this upper limit. So you need to find this area. Okay, so the integration that you have done before in your mathematics, in actual, is to find area under the graph. Okay, so how to find the integration based on numerical approach? We will start with the first technique that we call as trapezoidal rule. Okay, and this trapezoidal rule can be further divided into single and multiple. So I will talk first the first approach, which is single trapezoidal rule. So in single trapezoidal rule, so let's say this is the curve that you want to find the integration that is bounded by this curve, okay? And this is the upper limit. Sorry, this is the lower limit of your integral, and this is your upper limit of your integration. So in order to use single trapezoidal rule, we have to establish 2 points that is intersecting between the curve and the point here, the line of these lower limits, and another point that is intersecting of your curve and also these upper limits. To complete the development of the trapezoidal rule, we have to connect these 2 points by a straight line. Okay, so if I draw this line carefully, then you have a trapezium here. So basically, what you will use by using this trapezoidal rule, you will estimate the curve area by using this trapezoidal shape. So logically, if you see this diagram, this area is not representing the actual area. Why? Because you are not deducting this white area. Okay, so this method is not so accurate, but it can approximate the integration that you need by using single trapezoidal rule. However, this method is not so accurate. So in order to improve the problem of this integration, we will develop another method called as multiple trapezoidal rule, where the same area of that curve will be divided equally to equal number of trapezium. You see in this diagram, I divide this area into 3 equal trapezium, okay, where you may see that this is my first trapezium, okay, this is my second trapezium, and this is the third trapezium. They are having similar width, similar width. So in order to obtain the area, we can add up the first area due to the first trapezium, which is I1, plus the area contributed by the second trapezium, which is I2, and the last one contributed by the third trapezium, which is I3. If you see the diagram carefully, by using this approach, the error that is contributed by the curved line and also the straight line will be reduced. Why? Because you are dividing the area to a smaller part. That's why you can reduce the error. And if they say you want to improve the area approximation, you can further divide this same area maybe to 5 equal trapezium, 6, 7, 8, and up to number that you wanted, depending on the accuracy that you want to achieve for your problem. Okay, so hopefully you can understand the theory behind the trapezoidal rule, because once you know this theory, we can extend further on to find the formula. Okay, there's one step back before we develop the formula. We have to understand how to find the size of the interval, or usually denoted as h. Okay, so what is h? H is the size of the interval that is defined by this arrow. The size from x from equal to a until x equal to b for this diagram, and this is denoted by h. This diagram is for single trapezoidal rule. Okay, and the next diagram is denoted for multiple trapezoidal rule, where I divide the same area that you have in the first diagram to n numbers of equal trapezoidal. Okay, so what is h in this diagram? H is defined from this to this. This is your definition of h. So each of them will have similar h. Okay, and in order to find the formula for h for this multiple trapezoidal rule, the formula can be expressed as by deducting your upper limits with your lower limits and the number of equal interval n. Okay, and if we apply this formula to single trapezoidal rule, where the number of equal division here is only 1, therefore your h is only b minus a over 1, which is b minus a. So h for single trapezoidal rule is only b minus a, but h for multiple trapezoidal rule is b minus a over n. Okay, so the next slide after this is to develop the formula for area based on single trapezoidal rule and area for multiple trapezoidal rule. Okay, for single trapezoidal rule, if you still remember your Form 3 or Form 5 subjects, where you are given, let's say, a trapezium with certain width and certain height. Let's say I name the left side height is height 1 and the right side height is 2. Therefore, the area of this trapezium is only half of the width and times with the summation of height 1 plus with your height 2. Okay, so you can find the area of that trapezium using this formula. Therefore, I will apply this formula to the single trapezoidal rule diagram. This is your width of the trapezoid. This is the height of the left side of your trapezium. And you know that this is x is equal to a. Therefore, your height here will be fa. Okay. And if the upper limit is equal to b here, Therefore, the height of this will be FB. Okay, so therefore, the size, the area of this trapezium can be written by multiplying your half with the width, which is h, times with your height FA plus FB. And you know that h for single trapezoidal rule, if you still remember from the previous slide, is only b minus a, because the number of equal division is only 1, and multiplied by the addition of FA plus FB. So this is the formula that you may use to approximate the integration of from A until B of Fx dx for single trapezoidal rule. Okay. Is there any questions before we proceed with the multiple trapezoidal rule? Okay, if there is no question, we proceed to the next slide. How to approximate the area using multiple trapezoidal rule. Again, I will divide the same trapezoidal area to n equal areas. Okay, so you have 1, 2, 3, 4 until n equal division. I also name the first x value here to be x naught. Okay, so where your x naught is equal to a, x1, x2, x3 until xn. Okay, and in order to find the area, I think I have given to you the meaning of this. We can add up all of the areas from trapezium 1, trapezium 2, trapezium 3 until trapezium n, as you can see on this screen. And you know that in order to find your area for first trapezium, that is done by integrating your lower limits, which is x naught, until upper limits x1, and integrate this function that we call as fx. Okay, so this is given by this. Similarly, if we repeat the same approach for the second trapezium, for second trapezium, the lower limit is x1, so it is started by x1, and the upper limit is x2, and the function to be integrated over this region is also fx. Okay, and this is given by this expression, and you can repeat until to in. Okay? If you refer to the previous slides, you can substitute the corresponding formula for each trapezoidal rule, and by simplifying this formula, you will arrive to these final equations where you have term h here, that denotes the size of the interval, which is given by b minus e over n. And it is the formula states that I is equal to h over 2 multiplied by fx naught. Remember that this is your fx naught, because your x naught is here, plus 2 times the summation of when the indices start from 1, meaning that indices start from 1 here, until n minus 1, which is until these indices, you have to add up all of the height from 1, 2, 3 until n minus 1, and last one you add up the height of fxn, which is this one, this height, this is fxn. Okay, so that's how you obtain the formula for multiple trapezoidal rule. Okay, even if you do manually using simple trapezoidal rule and multiple trapezoidal rule, we still face the problem of having inaccurate value of integration. So that's why another person called as Simpson developed another method that we call it as Simpson 1/3 rule and Simpson 3/8 rule. And as I said before, this method can be subdivided into single and also multiple. For Simpson 1/3 rule, the same thing goes to Simpson 3/8, where we have single and multiple. Okay, so for this slide, I'm talking about single Simpson 1/3 rule and also single Simpson 3/8 rule. So what is the difference between single Simpson 1/3 rule with single trapezoidal rule? So what is the difference? So I will draw a graph here. This is your graph fx that is bounded from x0 until xn. So in single trapezoidal rule, you have established 2 points where you connect these 2 points by a line. Okay, that is how you develop the area using single trapezoidal rule. But in single Simpson 1/3 rule, Simpson add another point at the middle so that this point will divide the same area by 2 equal divisions. And the 3 points here will be connected by curve, not by straight line, but by a curve. And the curve is a polynomial curve with order of 2, with second order. Okay? So by using this and this midpoint, the area that will be approximated by this formula will be much more better than single trapezoidal rule. So in order to improve single Simpson 1/3 rule, Simpson also developed another method called as single Simpson 3/8 rule, where he adds another 2 interior points on the same area so that that point will be dividing the area equally into 3 divisions. And those 4 points will be connected by a curve, and that curve will be a polynomial curve. It's a polynomial function with third order. So you may get a better solution or more accurate area solution by using polynomial third order and adding up 2 interior points. Okay, the next slide will tell you how to obtain the formula for single Simpson 1/3 rule and single Simpson 3/8 rule. Okay, so this is the slide talking about single Simpson 1/3 rule. Okay, and you know that by that method, the area will be subdivided into 2 equal areas, which this is denoted by h, and this is also h, the width of that interval. And to find the h value, that is by deducting your upper limits and lower limits and divide by 2 equal division, because you have 2 equal division here. And if you refer to the textbooks, the area under the graph can be calculated by using this formula. Okay, and if you substitute your h here with with b minus a/2, then you can get another formula that only involving b minus a terms, and you may use either this formula or this formula to compute the integration based on single Simpson 1/3 rule. Okay. Okay, this slide talks about single Simpson 3/8 rule, where the area will be divided into 3 equal divisions, and each of the width is h. Okay, and to find your h, that will be b minus a over 3. 3 because we have 3 equal divisions, and that area can be computed by this formula. And if you substitute your h here to be b minus a over 3, then you can have this formula and to compute the area. So why the method have this 3/8? Because in this formula, you have 3/8 coefficient in front, so that's why the formula gets the name from these coefficients. Okay. So before we perform the multiple Simpson 1/3 rule and multiple Simpson 3/8 rule, I want to advise you something about on Octave coding, right? Because on Octave coding we have to perform some kind of modifications so that we can compute the value of integration in the correct manner. If you see carefully in this circle, okay, the first indices here, which is x0, that usually will be coded in Octave by x0. Okay, so in Octave, we cannot start our indices. This is our indices. Our indices start from 0. Right? We cannot start from 0, but we must start our index by 1. Okay, so I have to change this to be fx1. Okay, and this x1 we have now to shift to be x2. So this will be your x2. This will be x3. This will be x4. This is only applies in Octave coding. So the same thing also goes to the previous formula here for Simpson 1/3 rule. This will be x1. This have to change to be x2, and you have to change it to be x3. Each of the indices will be shifted by 1. If we refer back to trapezoidal, okay, so it is good if I erase this. So I have to change this to be x1 because 0 is not accepted by Octave. And these indices, which is started from 1, have to be changed to 2. And this index from n minus 1, I have to change it to be, by adding up by 1, that will be until n. Yeah? And this index have to change to be n plus 1. All of the index again have to be shifted by 1. Okay. So similarly for this one, but this one I will talk later on. So now I will do the explanation on multiple Simpson 1/3 rule. Okay. Multiple Simpson 1/3 rule. And in this multiple Simpson 1/3 rule, we will divide our integration area. Let's say this is your graph in the multiple of 2. Right? So you can divide your area by this Simpson 1/3 rule, maybe to 2 divisions, 4 divisions, 6 divisions, until to 2n divisions. Yeah? Because 2n stands for multiple of 2. So maybe I can divide this area into 4 equals area, and that is allowed in this method, where you can divide the area into multiple of 2, where each of this is h. This is h, this is h, this is also h, and h is defined by deducting your upper limits, which is your b here, and your lower limit, which is a there, with the number of intervals. Your interval must be in the multiple of 2. So by using this equation and simplify that expression, then you can use this formula to compute the multiple Simpson 1/3 rule. Again, remember, x0 cannot be used in the octave, so I have to change this to be x1. This index you have to change by adding each of them by 1, so this will start by 2, 4, 6. This will be changed to n. This will be changed to 3, 5, 7. This have to change to be n minus 1. And also this have to change to xn plus 1. Okay, this is only applicable in Octave or MATLAB. Okay, for the last formula, multiple Simpson 3/8 rule, we can divide the area in the multiple of 3, 3n. So you can divide your area, let's say, to 6. 1, 2, 3, 4, 5, 6. Let's say all are the same. So you can divide into multiple of 3. And remember that your h, that is defined here, h, and so on, is given by this formula, where n is the multiple of 3. And this is the formula that you should understand in order to compute the integration of a until b for your fx by using multiple Simpson 3/8 rule. And again, you have to perform shifting on each of the index on your own. I don't want to repeat it again. And we can use Octave to perform that integration. Okay, to make yourself understand, especially in MATLAB coding or Octave coding, I'll give you one example of integration where I use a very complicated equation for integrand. This is your fx. Okay, your fx is 2000 ln 140,000 divided by 140,000 minus 2100x, close the bracket, minus 9.81x, where the lower limit is to be 8 and the upper limit is 30. Okay. In order to compare the exact solution of this, I have already done the calculation using your calculator only. Your scientific calculator can perform integration. So the exact solution is 11,061.34. Okay, so we want to use single trapezoidal rule. We want to use multiple trapezoidal rule. We want to use single Simpson 1/3 rule. You want to use multiple Simpson 1/3 rule. And the last one is single Simpson 3/8 rule and multiple Simpson 3/8 rule. So we have to use 6 methods, and we want to compare with this, whether this method is accurate or not. So to start with the solution, I will use Octave. I will open my Octave. And this is the Octave that I've coded already for you. So as usual, we will clear the screen, the CLC, clear the memory, and also close any figures. And I will establish the lower limits, which is 8. And the upper limits of the integration to be 30. And I'll start with my number of interval to be 1. And this is the function that I want to integrate. I'll put in terms of function here, f. And to compare, I will put my exact value of integration to be here. Okay, so we start with a single trapezoidal rule. So in this line, I will define the h value, the width of that trapezoidal rule, which is b minus a. And I will define the x value that is defining your x coordinates. Okay. And by using the formula that you have before, okay, which is this formula, half of b minus a times fa plus fb. So I put in this line, okay, and I will compute the error. Okay? So the error will be computed by, so how to find the error? So I will find the true error, the percentage of true error, by taking the absolute of the exact solution minus the approximate solution divided by exact and multiplied by 100. Okay? So this is how I get my percentage of true error by deducting your exact with the approximate and divide back by exact times 100. Okay, so that is coded in Octave by this line. So I want to see the output of this while we run this and see what is the output. So this is the output. You may see that by using single trapezoidal rule, the area is 11,868, okay? Whereas the exact value of the integration is 11,061. So this already agreed with our hypothesis, stating that by using single trapezoidal rule, it is not so accurate because it is because you already estimate the graph by using only straight line. So the error in by using single trapezoidal rule is about 7.3%. Okay, so in order to improve this integration, we will discover the next method that we call as multiple trapezoidal rule. Okay, where I put my h here to be b minus a over n. Remember that your your h for multiple trapezoidal rule is b minus a over n, which is given here. So I code here, and my x, the x coordinate will be given by this, and I will code my area of trapezoidal using multiple method by using this line of code, and at the bottom of it I compute the error. And let's say we try to use let's say 2 division, let's say, because the first one is using 1 division only. Okay, now I change to 2 equal divisions and see what is the output. Okay, by using multiple trapezoidal rule and using 2 equal divisions, the area is quite improved, because the area now is estimated to be 11,266, where the exact value is 11,061. And the area is quite small, compared to the first one, which is 7%, now is reduced to be 1.8%. But I'm not still satisfied with this value because the area is still large. So what you can do, maybe I can change the value of the divisions here. Maybe from 2, I change it to be 6. Okay? And I will run it again, see what will the output. Okay, so the error is reduced from 1.8% now is to be very small, which is 0.2. And the area is estimated to be 11,084. But I'm not still satisfied, so maybe I change that interval maybe to, let's say, 40. So we'll divide the area to be much more smaller by 40 equal divisions. and see what will be the output. So the error is very, very small. From 0.2 now, it's reduced to 0.0046, where the approximate area is 11,061, and the exact value is 1161, which is almost the same. And maybe you can improve further on by increasing the number of the division. But you may see that in order to get a better solution, I have to ask Octave to use a very large value of equal division. So that's why not we use another method called as Simpson 1/3 rule, where you divide the area by 2 divisions. Remember this, 2 divisions, where the formula of H is equal to B minus A over 2. Okay, and this is the formula to find the area. So I put all of that code in this line. So B minus A over N, where my N is 2. And this is the formula to find the area by using Simpson 1/3 rule. So I will run this based on 2 division and check what is the answer. You may see that just only by using 2 equal division and using single 1/3 rule, you can get a very small error. But if you compare with multiple trapezoidal rule, you need to use a very large N value, then you get a very small error. So by using 2 only, you get a very small error. So it's very good to use Simpson 1/3 method. And if let's say I want to improve my solution, why not we use the next method called as Simpson 1/3 multiple, and that has been discovered here. Multiple Simpson 1/3 rule, where the number of N here must be multiple of 2. So I have coded that in this. Okay, so I will, let's say I'm using from a multiple of 2, let's say 4, and see what will happen if I run this code. So by just using 4, you get a very small error. So this error is almost the same with the trapezoidal rule, but you need a very large value of N, 40. But here you just need only 4, very small divisions, but you achieve a very small error, and the area is quite similar with the exact. So maybe if you want to improve, so I will use the multiple of 2. Let's say this to be 10. Let's say you use 10 and see what is the output. So just using 10, you get a very small error. 1, 2, 3, 4. 4 zeros in front. Just using 10. The error is very small compared to trapezoidal method, where you have to use 40. Where is it? 40. And the error is not so small. It's only 00. But here I'm using 10 equal division, but the error is quite small. Okay, so you can experiment it using other multiple of 2. Next, we want to discuss for Simpson 3/8. Simpson 3/8 single. Where is it? I think this. This is the lecture. So the area is divided into 3. 3 equal of division. So you may see that this is N is equal to 3, and I'm using the formula. This formula. So if I run this by using 3 equal division, let's see what is the output. So by using 3 equal division, the error is small, it's quite small, and the answer is almost equal to the exact, because the exact is 11061. It's almost. So in order to improve, we can use the next method called as Simpson 3/8 multiple, where you can use multiple of 3. So maybe I will change this to be 6 multiple of 3. And I will run this code. So by using 6, the array is small, it's very small. And let's say if I want to use, let's say 9, multiple of 3, then you see that by using 9, the array is quite small. If you compare with the Simpson 1/3 rule, you need 10. Then you get a very small error. But using Simpson 3/8 rule, multiple, by just using 9, you can get a very small error. So that's how you can use Simpson and trapezoid in order to solve your integration problem. So, do you have any questions? Do you have any questions? Apa dia? Saya tak dengar.
No, sir.
Apa dia? Saya tak dengar. Tak jelas suara awak. Boleh ulang soalan awak? Saya tak tahu jelas. Ada soalan tak setakat ni?
Tak ada, sir.
Okey, kalau tak ada, kita stop setakat ini saja. Dan saya berharap sangat assignment tolong hantar ya. Lewat sikit tak apa. Saya bagi kebenaran sampai hari Jumaat ni you boleh hantar untuk yang assignment ke fitting. Dan minggu ni juga saya akan bagi assignment untuk ODE. So ODE ni nanti hantar lagi 2 minggu. Maybe masa tu dalam minggu raya kot. Tapi maybe lepas raya you hantar pun tak apalah. Okay, never mind. After this, I will give you the Google link untuk attendance dalam WhatsApp, so that you can use that for attendance. So if there is no question, I stop my lecture and selamat berbuka puasa. Okay? Okay, Assalamualaikum warahmatullahi wabarakatuh.
Okay, sir.
Thank you, sir. Assalamualaikum.
Waalaikumsalam.
Assalamualaikum.